Hello everyone, and thank you for joining me for this virtual presentation. I'm sorry I can't be there in person live to deliver this, but as we're all accustomed to in the current circumstances, sometimes these virtual presentations are just as effective. As you can see, the presentation is on the theme of change detection. We're going to be taking a look at a couple of scenarios, a couple of examples of how we can detect or analyze change using point cloud data, lidar data, if you're more familiar with that format. Before I can begin, quick introduction. My name is David McKittrick. I am the Outreach and Training Manager at a company called Blue Marble Geographics. We are a software development company headquartered pretty much as far away from you folks as we can get. We're in the northeast of the US, in the state of Maine. We produce a number of products, including a product called Global Mapper. Some of you may be familiar with that. I'm actually going to be using that a little bit later to illustrate some of the points that we'll be covering in regard to looking at change detection within point cloud data. A quick overview of my plan here. What I'll be hoping to do in the next 25 minutes or thereabouts. Well, first we're going to address the question of why. We are finding an increased use of this type of technology to detect change where has change occurred. It's worthwhile pausing before we actually look at some practical examples to answer that question as to why that is the case. Why are we seeing that as a more important component of our geospatial analysis than it was in the past? We'll look at a few different ways we can address the idea of detecting change, and the most simple of those is just visual. As we go through a couple of scenarios, we'll take a look at how we can simply visualize our data or change the display characteristics, alter how our display looks to make that change a little bit more apparent. So sometimes simple visual analysis will give you the information you need. Beyond that, we'll look at a couple of examples at different scales using point cloud data. In fact, using two point cloud layers. We'll look at a couple of examples of how we can actually gauge change or even detect change where it has occurred at a very, very localized level. Now, the first of those, as you note here on my bullet, is change detection at a micro scale. In this, we're going to take a look at a situation where we can find individual points that have been moved in some way. Now, maybe practical examples of this may be in maybe an agricultural setting where you're looking at how much growth has occurred. The workflow in this case is going to allow us to identify specific points that are offset by a prescribed amount, or at least a prescribed amount. So it will isolate points that have shown some level of change. And again, we're going to take a look at this one. Again, that, as I mentioned, determination of acceptable threshold beyond which that change is considered significant. We can establish what that is. Again, this is most applicable at a micro scale, looking up close at some of those minute changes that you may encounter. Moving to the other opposite end of the spectrum, we're going to look at change on a macro scale. In fact, for this example, we'll take a look at an urban environment, and what we want to try to detect in that context are buildings that have been added or buildings that have been removed. Obviously, identifying individual points that have moved may not be the most appropriate workflow. So what we're going to do in this case is we're actually going to generate a raster surface from our point cloud. We're going to grid it. Many of you, I'm sure, are familiar with this workflow when it comes to generating a DTM, a digital terrain model. We're going to apply a variation on that theme in this workflow because we're going to generate what's called a DSM, a surface model. We're going to take the entire point cloud layer, generate a raster version of that for the two time frames that we're going to be considering, and quite literally we're going to subtract one from the other, and that should hopefully give us a very interesting visualization of not only where changes occurred, but also in this case, the extent of change, how much change has occurred within those localized areas. Again, calculating and visualizing the difference between our surfaces. Before we get to those practical examples, let's take a look at, or answer the question, I should say. Let's answer the question, why are we seeing this? Why has change detection become much more prevalent? And certainly we're finding this in our company, that people are approaching us with this specific question. Why, with this point cloud data that I've collected, how do I determine the offset between the two? Perhaps seasonal variation or year-over-year variation. Well, probably the most important reason is the rapid expansion on data availability. I mentioned earlier, we're working with point cloud data. LiDAR is probably the format specifically that many of you are familiar with. When I first started working with LiDAR data many years ago, it was very much a luxury commodity, and it was very often collected as a one-off process. Today, it can be collected virtually on demand. Certainly, the cost of LiDAR collection, the size of the necessary hardware has been reduced. All of these factors are lending themselves to this on-demand data collection. So you can send a drone up with a LiDAR collection platform and collect data virtually in real time. So you can analyze that seasonal variation, or perhaps in an engineering project, you can see where that shifting may have occurred between one time frame and the other. So availability of data is important. I have been referencing LiDAR data. Obviously, there are other point cloud formats. There are other methods for generating point cloud data, including a photogrammetric process. Again, the fact that that is now readily available technology means you can go out and collect data or process your imagery or images to generate that point cloud and perform this type of analysis on an as-needed basis. Tied in with that is the emergence of easy-to-use tools to analyze this data. I'm going to do a little bit of promotion here, but we're going to be using Global Mapper as an example now. Disclaimer, that's obviously not the only application. There are many, many tools out there that will let you work with this point cloud data and process it and analyze it and determine differences between two timeframes, or maybe even correcting some of those differences if you've collected data in different timeframes and they need to match up. There are processes, obviously, for allowing you to merge them together to make sure they line up correctly. So addressing offset of data it has become readily available in some of the tools that are out there. And final bullet here, and this is an important one as well, there is an increased awareness that change is not always good. Yes, there are going to be situations where you analyze change to see how much growth there has been, maybe in a forestry situation, or I mentioned agricultural applications. But seeing change where change is not expected or not welcome is another reason to embark on this type of project. Again, I mentioned engineering applications. Is there a significant shifting in maybe a dam, an earthwork dam, or some structural shifting in some of the transportation infrastructure? Things like that can now be detected at the point level. So there is an increased awareness that this type of change is something we should be monitoring. And again, based on the fact that our data is available and we have technology, this is something that's becoming much more prevalent. So some examples of the industries, businesses, kind of functional areas where we're seeing this increase in this idea of change detection. Agricultural production, I've referenced that a couple of times already. Agriculture has changed dramatically. I don't know, I don't need to tell you folks this, but in the agricultural field, no pun intended, we're seeing a lot of technology being applied. GPS-based agriculture has become very common. My father was a farmer back in the day, and certainly he looks at some of the technologies available now and says, wow, if only I had those tools back then, I could have done a much better job. Being able to detect change in growth patterns, assigning or applying fertilizer and irrigation accordingly makes us more intelligent. Tree growth. I mentioned the company I work for here in the state of Maine. 90% of the state is forested, as is a very large percentage of your part of the world as well. And the technology we have now to monitor tree growth for productivity, for harvesting, pre-harvesting analysis. Point cloud analysis is playing a major part of that in the change, seasonal change or year-over-year change. Geomorphological shifting. I embarked on a project close to the coast here, or close to where I'm sitting, on the coast of Maine, to look at some of the localized changes along the coast. Readily available on-demand collection of point cloud data was the basis of that analysis, where I could detect changes in the coastal morphology based on a time frame, an applied time frame within which I had that data. Engineering, infrastructure, maintenance, I mentioned that one. We'll take a look at this specific one as a practical example. The urban landscape is obviously evolving. Tied into that is regulatory enforcement. I jumped ahead a little bit here. Are the buildings that you're seeing, are the increases in your Z value in your surface models reflecting what has been approved as far as regulatory compliance is concerned? Being able to analyze point cloud data overflown in an urban environment will give you a clear picture of where changes occurred, either buildings or even vegetation. Where have trees been removed that we weren't aware of? And we'll, again, take a look at that example in a minute. Going back one bullet, environmental degradation, obviously in the natural world as well. Some of the changes that we were able to detect may be a reflection of the natural world or the health of the natural world. Changes that reflect inconsistencies in the data collection process. I alluded to this a few minutes ago as well, where perhaps changes a difference in the elevation value in two timeframes based on maybe different collection methods. Where change is not necessarily something you want to detect or measure, but something you need to correct. The older data maybe is not as accurate. Maybe it's referenced to a different datum. So that idea of detecting how much offset there is may lead to some sort of correction process applied to one or other of the point cloud data sets. Same procedure in terms of analyzing, determining that change, but obviously with a different outcome. Now, the final bullet I put in here at the last minute, we tend to think of point cloud data as a representation of elevation, and in 99% of the time that will be the case. But we can model data in a similar way that's not necessarily elevation. We can take a point-based database and grid it, create a surface, whatever we need. Those values can be analyzed in the same way that as if they were elevation. So you can see offsets. And again, think of maybe a surface referencing perhaps rainfall. Just a crude example where we can now detect offsets between seasonal rainfall, year over year, etc. Where our point data is not an elevation, but is a measure of the amount of rainfall, we can apply the same procedures we're about to see today based on that non-elevation type data. So that by way of introduction. Most of my presentation, I'm going to be roll my sleeves up and do a little hands-on demonstration here. So I'm going to fire up some software where we can actually take a look at some of these applications at work. So as I mentioned, I'm going to be using a piece of software called Global Mapper. This is Global Mapper Pro version 23. Those of you who are interested. And the first example, the first workflow, as I mentioned during my introduction, involves analysis of a point cloud at a very localized level. Now, I actually have two separate point clouds on my map view here. Actually, I got one displayed right now. They cover the same area. If I turn the other one off and the other one on, they are, again, have the same coverage. Looking at my scale, if you note right at the bottom here, we're not dealing with a very large area. It's about just over a meter wide, maybe a couple of meters tall. So this is a very localized point cloud. It is a point cloud. It is a laser scan derived point cloud file. Now, the resolution of the data is probably a little bit higher than you're typically used to dealing with. There's about 1 million points per square meter in this example. In fact, if I zoom in a little closer here, we'll start to see some of those points. So yes, they're very closely spaced. I'm going to go back out again. Now, it may not be immediately apparent what we're looking at here. The visualization of my data is representing the elevation. I'm not looking at the legend right now. I don't have that displayed, but those color patterns you see reflecting in the texture of the point cloud are an indication of elevation. To make this a little more meaningful, I'm going to change that visualization to view by RGB. There are colors present in this point cloud, as you can no doubt see now. This is a pebble field. And this data, while it may not represent a practical application for this technology or this particular scenario, it does give a very good illustration of how this technology works. Because again, as I mentioned, what we're going to do in this first scenario is we're going to identify individual points that have moved when we compare one point cloud with the other. One of the other my bullets is worth noting as well, because I mentioned that change detection may be visual. In this little exercise, when this data was collected, and obviously two separate point clouds, between the two collection processes, 3 pebbles were removed. Now, in this exercise, we're going to isolate those pebbles. We're going to see which pebbles are missing from the second of the 2 passes. But obviously, there's a simpler way of doing this. This is cheating a little bit here, but you'll see by simply turning on or off the specific layers, we can start to get an idea as to where that change has occurred. Now, it is an important component of change detection, simply looking at your data, doing a a alternating view, if you like, and maybe even drawing a profile. I'm very quickly going to draw a cross section here of a specific width that's a little bit too wide. Now I'm going to bring this down to about 10 centimeters in width, and I'm just going to draw a cross-sectional view here, hopefully in that process a little bit offset here, but you can start to see again when we enable and disable the two layers, and hopefully you're getting a view there, we can start to see some of those changes. And this lateral cross-sectional view is sometimes the best way to see some of those changes between one pass and another. If I was looking at two different lidar files in this case, seeing where that offset is much easier looking at it from this lateral or this cross-sectional perspective. So visual analysis is important. However, what we want to do is isolate the points that have changed. We know changes occurred. We saw that in our quick back and forth, but we want to see specifically where that change has occurred. The tool that I'm going to use for that is one of the options right here in the lidar toolbar in Global Mapper Pro. It is called Compare Point Clouds, and it does exactly as it implies here. We simply run through a process, and with apologies, I'm not going to dwell on the settings here, but we run through a process of comparing one of these passes to the other. We define the threshold offset, how much change is significant. In this case, we're dealing with meters, and obviously we're dealing with a very localized area. So I'm going to keep this fairly narrow, very tight, if you like. 1 centimeter of offset is all I'm interested in. Any less movement, I don't care. When we compare the 2 point clouds, if that movement has been a few millimeters, I'm not concerned. This is only going to address 1 centimeter or greater in terms of change. For us to consider that change to be significant, we need at least 50 points within that local neighborhood, a clustering, if you like, to have been changed, and that's what will apply. Now, hopefully this will give us, when we run through the process, an indication of where that change has in fact occurred. It's literally looking at every point, looking at the corresponding point geometrically in the other point cloud, and isolating the shift. Noting that it has identified over 34,000 points that have fallen into that criteria, that are offset by that amount. It also has selected them, and it has created a new layer. So this is my change layer. What I've isolated here, and obviously, again, you can see quite clearly the significant changes right in the middle of my screen. A little bit of a change along the periphery. My assumption is that whoever reached in and removed the 3 pebbles also dislodged a couple of pebbles along the edge. So that offset was also detected. But obviously, in the more focused area that we're looking at, it's quite clear to see where that change has occurred. We have isolated the individual points that have demonstrated a degree of change that is significant in our eyes. What we didn't get from this analysis is the degree of change. There's no way to know how much change there's been. Yes, we know it's beyond that threshold, but it's simply identifying the geographic area of change. In our next scenario, we're going to take a look at a different scale of change detection, obviously a much larger area, but we're also going to determine how much change has occurred. So in this example, we have some imagery on the screen. This, to give you a little bit of geographic perspective, is the city of Portland, Maine, some of the downtown area of the city. Northeast US, about 2 hours north of Boston, if you want a more precise geographic location. This area is what's often referred to as the Old Port, or kind of the Eastern Prom. This is obviously surrounded by water, as you can see here. So for this area, we have 2 point clouds. You may have seen over here on the left side, we have a 2006 point cloud. I've already done a little filtering and cleanup. Just reflecting all of the features. We haven't isolated any particular type of point, ground, etc. We've retained all of the points in the point cloud. So we have a pass 2006. We have another pass at 2015. This is a higher resolution point cloud. You may see where my cursor is located. It actually pops up the point count, 23 million for 2015, 4 million for 2006. Obviously, advancing technology, higher resolution data available. 2015, that was not available, 9 years previous. But this is the raw material for another example of change detection. Obviously, we're looking at an urban environment. Our objective in this exercise is to determine where buildings have been built, or indeed where buildings have been removed. We'll also get some additional information about vegetation, although that's not our primary focus. We'll see where trees have grown, hopefully, and maybe even trees that have been removed. As I mentioned, the best way to approach this type of change detection is not using the same procedure I did before, because obviously determining that degree of offset is going to just give us points. We'll just have a collection of points that have demonstrated some type of shift. Yeah, maybe it will isolate those buildings, but I think a more meaningful analysis in this example is to determine the level of change. How much change has there been? How much growth has there been, perhaps in the tree canopy, or buildings? How tall are the new buildings that have been built? So those are the questions that we're going to answer. And as I mentioned, we're going to answer those questions by performing a mathematical procedure, not on the point cloud, but on a gridded representation, a raster representation of that point cloud. So what I'm going to do, I'm going to take the 2015 layer, and I'm going to go through a process of creating a grid. Now, we typically apply this for generating what's referred to as a DTM, a terrain model. And that would be a model which obviously reflects bare earth. You're going to use just the ground points, generating your nice surface for contour generation, volume calculation, whatever else you need to do. In this case, I'm not going to apply the filter. We're going to retain all the points, and we're generating what's called a DSM. I'm going to make sure I name this layer appropriately because I often forget. So it's 2015 DSM to give it a correct name. We're generating a new raster layer. Again, not dwelling on the details here. I'm going to manually define the resolution of my output, about a meter output. You will notice, by the way, I've already done this once already for the other time frame, so I'm just going to go through this process once. I think that's all I need to do in here. Click OK. Shouldn't take long. When it completes, we will see a new layer listed here. Now, that's really all the function that the point cloud has. I don't need it anymore. It has served its role. It's given me the raw material for my surface layer. I'm going to turn on the original that I created previously. This feels a little bit like a cooking show. The dish that I prepared earlier, the 2006 version, which was already there. Now, again, we have two versions of a raster surface derived from two separate point cloud layers. Again, as I mentioned, one of my bullets in the introduction was visual comparison. Here's an example where we can take a look by simply turning one layer off where changes occurred. Now, those of you who are glancing around as I'm doing this can quite clearly see where there have been changes, where buildings have been built. I'm going to point you right here. I don't know if you're seeing where my cursor is located. It's on lower left corner, south west corner of the screen here. You can see that building. If I turn off the 2015 model, was not there in 2006. So there obviously has been changes here that we're going to take a look at in a more methodical way in just a second. Another very interesting tool that's available is what we refer to as image swipe. Image swipe allows us to pull back a raster layer to see what's underneath. Now, it may not be immediately apparent what I'm doing here. Maybe if you follow my cursor up and down across the screen, it's almost like I'm pulling back the curtains to see what's underneath. And again, this is a very useful tool to do that back and forth comparison. I'm going to go top to bottom, left to right, whatever. Again, it's quite difficult to see because the two layers look the same, but I'm pulling back one to see what's underneath. So again, as an initial analysis, I may take a look at the data to target areas where I can see that type of change has occurred. When I'm ready, I can actually perform the offset analysis. And again, because we're dealing with raster data, we're going to use a different tool. We're going to use a mathematical tool. This is effectively a raster calculation process, because every pixel in these raster layers now has value. They have elevations. It's a z value per pixel. I can conduct a simple comparison. I'm just going to call the output layer that I'm generating difference. NCE, if I spell it correctly, I did. And then I can apply an operation. This is literally going to compare pixels that sit on top of other pixels, the two layers I'm working with. I can add them together. I can find the average or minimum or maximum between the two, or I can subtract. And two variations on that are signed and unsigned. I'm going to use signed in this case because I do want to know if change has been positive or negative. If we just wanted a whole number offset, we wouldn't worry about that. We would leave it unsigned. But I want a signed offset in this case. I'm going to take my 2015, I'm going to subtract my 2006, and I'm going to make the shader, the visual representation, inherit the same color pattern that we have here initially. I'm going to change that, as you'll see in just a second. But again, quickly clicking this, it's a quick mathematical process. Generating as an output a new layer. Let me turn off the original 2 here. Now, it's not immediately clear, overly clear, what exactly I'm seeing here. Maybe you are seeing a few different shades, but because this is applying the same texture pattern, the same color pattern, it's not really accentuating the surface differences. What I'm going to do is I'm going to apply a new shader. I actually built this shader, this color pattern specifically for this purpose. I call it difference, as you can see, and that more clearly illustrates where we're seeing change between those 2 original point cloud layers. Again, glancing at my legend here, you can see how this shader was applied. Increasing intensity of red color shows positive change. Buildings that were added effectively is what we're looking at here. Areas of blue, you're looking at either buildings or indeed trees that are likely to have been removed or cut down. So those are the 2 distinct colors, and I could obviously have changed these colors in whatever way I want. Areas in white, no change. That's what the kind of the takeaway from this is. And again, quite clearly in this example, as I pointed out before, we can see how much change has occurred right down here at the bottom of my screen. In fact, if you look at my cursor location, and if I point you down to the bottom corner of my screen, you can see I can even tell that that building is about 42 meters tall. Moving around a little bit, I can see again where some in the areas of blue where some trees perhaps have been removed, and we can see where a building has been removed here as well. So this 9-meter tall building was removed. I have looked at it before, and I believe this was actually removed to create a parking lot. Yeah, you can see that right here. Excuse me while I zoom in a little closer here. So there was a former building here, and you can see in my difference model that obviously that was removed to accommodate a parking lot for, I think, a new hotel right next door. I could continue to tell the story here. But by the way, you may notice these shadows around some of the buildings. That's simply a consequence of the fact that the 2 flight lines were slightly offset. So we're getting one side of the building from one flight line, another side of the building from the other time frame, and that's why you're seeing that difference. I'm not concerned about these rings around the buildings, obviously. In fact, I could run a query to remove those using another process. But obviously, visually targeting the areas of most interest, it's quite clear to see where significant change occurred by comparing these 2 DSM layers. So my time is almost up. A quick recap of some of the themes we dealt with. 2 primary examples of change detection, 3 if you include the visual analysis I mentioned at the start. But change detection on a micro scale, again, looking at where individual points are offset beyond that defined threshold. Change detection at a macro scale, using a surface model, transforming your point cloud into a raster layer, giving you the basis thereafter of conducting a simple mathematical calculation. Applicable in certain situations, obviously, where just identifying points is probably not appropriate. Thank you very much for taking the time to attend and to listen to my presentation. Hopefully you found the presentation useful. If you have questions long term, I'm going to suggest you jot this email down. This is my tech colleagues here in the company, geohelp@bluemarblegeo.com, and they'd be more than happy to answer any questions you have about this technology, about the workflow. If you are using this email, I do suggest you mention that you attended the conference and that you have a question in reference to this presentation. That way they'll know what you're talking about. So hopefully they find this useful. Thank you once again for taking the time, and I hope the rest of the conference is great for you.
Thank you so much for that presentation. I'm
Welcome.
a big Global Mapper fan.
Delighted to hear it.
From a long time. I've definitely been using Global Mapper for over, that'll be 23 years now.
Wow, you're a veteran.
We used it at COGS in Nova Scotia. They had it available to us there. And we were using it a lot at the time for transformations, reprojections, and stuff like that. It's certainly come a long way.
It definitely has. In 23 years, it's a completely different application now. It continues to evolve. Absolutely.
Fantastic. We've got a little bit of time for Q&A. We've got a question in already. Folks, get your questions in right away if you want to get in on this. I see a comment from Ted, who I know is a lidar guy that I worked with many years ago. He works with NRCan. Very interesting tools. Thanks, Ted. There's another question. Will change detection work with photogrammetrically derived point? derived point cloud data? I don't know if I mangled that or not.
No, I think it's a hard one to say. Yeah. So yeah, I think I referenced earlier in the presentation that the tools will work with any point cloud data, and there's actually a tool within Global Mapper for generating photogrammetric point cloud. So the answer is yes. Regardless of the point cloud source, the tools we saw, and in fact, all the lidar analysis tools will work with any data that you import into Global Mapper. Yes. Answer is yes.
Cool. We've got a great question from Irene. 3D point cloud is highly dense. Low resolution points are disconnected when zooming in. Since the metaverse/digital twin trend is on the rise, how do you see the increasing internet technology, e.g. bandwidth and latency, catch up with the vast amount of point cloud generation in order to maintain satisfactory user visualization?
Oh, that's quite a question. I have it in front of me as well. Let me see if I'm getting the points here. Yeah, I mean, obviously point cloud size is an issue. And we're talking here about internet technology. I'm not sure necessarily that that's going to be relevant in terms of what I was showing. All of the files that I was referencing were locally stored, but it is something that our development staff are very aware of in terms of the size of the point clouds. The largest point cloud I've worked with in Global Mapper has had 3.5 billion points. There is no limit in terms of what Global Mapper can process. So yes, we are very aware of that, the increasing size of point cloud, and we're making our development reflect that as well. So yeah.
Fantastic. Another question coming in from Susan. This technology would be so useful, areas north of 60, where it can be prohibitively expensive to obtain data. Would you have any recommendations for solutions to handle these vast remote areas?
Data acquisition is not my field. Obviously, the data I was using was provided, government agencies collected, but yeah, you go into remote areas, access to data is an issue. I think what we're finding, just based on folks who use our technology, is the technology that is required to collect this data is becoming more, I use the term accessible both from a technical point of view, also from a financial point of view. And we're seeing an increasing use of unmanned aircraft, drones, UAVs, whatever you want to call them, for that data collection, especially when it's required for on-demand data acquisition. You can deploy lidar collection on a drone. It is still quite expensive. The alternative is to generate your point cloud, and we've referenced this terminology already, photogrammetrically, using structure for motion. So if you are in a remote area and you have access to a UAV or a drone, you can effectively create your own 3D data just simply by collecting images. There's a process embedded in Global Mapper that will analyze those overlapping images and generate that 3D data for you. So now that may be a solution to those areas where, yeah, you're dealing with a vast area and, more remote, and there's no data available.
Thank you very much, David. David, we're into our break. Any closing points you wanted to make to the community? Anything you wanted to share before we move on?
Just thanks for all of you folks who paid attention and the comments and questions that came in. I did throw an email address on the final slide. I don't know if you had a chance to jot that one down, but if you have any questions, the best way to get in touch of the company here is geohelp@bluemarblegeo.com. I believe the recordings of these presentations will be available. If you're obviously watching the recordings, again, you can follow up with us. Let the folks know what your questions based on, the fact that you're the conference, and we'll be more than happy to answer those questions for you.